Magnetism is literally everywhere. I mean, from the enormous magnetic fields that stretch across entire galaxies, all the way down to the tiny, invisible atoms that make up you and me. It's one of the most fundamental forces in the universe. But for something so common, it holds on to this one really deep, fascinating mystery. One you've probably even wondered about yourself.
Think about it. We've all played with magnets, right? But have you ever tried this? You take a bar magnet, you snap it in half, hoping to get a pure North Pole in one hand and a pure South Pole in the other. But that never happens. You just get two new, smaller magnets, and each one has its own North and South Pole. So why? What is the fundamental rule of the universe that stops us from ever finding a North Pole all by itself?
Okay, so to really unpack that question, we've got to get on the same page about what magnets are and how they work. Let's start with the basics, the stuff people figured out centuries ago, way before we had the physics to explain any of it.
So these simple observations, they really start to paint a picture. We know our whole planet is basically a giant magnet. That's why a compass works. We know the basic rules. Opposites attract, likes repel. Simple enough? But it's that fourth point that's the real head-scratcher. The fact that you just can't seem to isolate a single pole. That's the clue, right there. That's the thread we're going to pull on.
So where does magnetism even come from? Well, the first huge breakthrough was realizing that a plain old bar magnet looks and acts almost exactly like a solenoid, which is really just a fancy name for a coil of wire with electricity running through it. This was a game changer. It suggested that all magnetism, even in a chunk of rock, is really caused by moving charges, countless microscopic currents, all circulating and swirling around at the atomic level.
All right, so if magnetism is all about these tiny moving charges, how can we possibly visualize its effect? I mean, it's invisible. Well, to really understand a magnet, we have to find a way to map that invisible field of force that surrounds it. And the way we do that is with something called magnetic field lines. Just think of them as a contour map for magnetism. Now, of course, they aren't real lines floating in space, but they're an absolutely brilliant tool for helping us see the direction and the strength of the magnetic force all around an object.
And these lines, they don't just go wherever they feel like it. Oh no, they follow four very specific rules. First, and this is the most important one, they always form continuous closed loops. Second, the direction of the line at any point tells you exactly which way a compass needle would point. Third, wherever the lines are bunched up close together, the field is strong. Where they're spread out, it's weak. And finally, they can never, ever cross each other. And right here, this is where you see the huge fundamental difference between magnetism and electricity. See, electric field lines have a clear beginning and a clear end. They start on a positive charge and they stop on a negative charge. But magnetic field lines, they have no beginning and no end. They just loop continuously from the north to the south pole on the outside, and then, get this, from the south back to the north on the inside of the magnet. This is a massive clue.
So, the fact that these lines always form perfect, closed loops isn't just some quirky little detail. It's actually the picture book version of a fundamental law of physics. It's the law that's going to finally answer our big question.
It's called Gauss's law for magnetism. And what it says in plain English is this. If you imagine drawing any kind of closed shape, a sphere, a box, whatever, around a magnetic source, the number of field lines going out of that shape will always be exactly equal to the number of field lines going in. The net result, the net flux, is always zero.
And this is the fancy mathematical way of saying the same thing. What this equation is really telling us is that you can never trap a source or a sink of magnetism inside your imaginary box. Because if you could trap, say, a lone North Pole, you'd have more lines leaving the box than entering it, and the total wouldn't be zero.
And that's the whole ballgame. Gauss's law for magnetism is the universe's way of saying there are no such things as magnetic monopoles. There are no lonely norths or isolated souths. The simplest, most fundamental magnetic thing that can exist is a dipole, a north and a south pole stuck together forever.
Okay, so we know magnetic fields are made by moving charges, and their field lines always form closed loops. Awesome. But now let's switch gears. What actually happens when we take different kinds of materials and stick them inside one of these magnetic fields? How do they react?
So to talk about this, we need a few new ideas. First up is magnetization, which we call M. The best way to think about M is as the material's internal reaction. When you hit it with the magnetic field, you're basically trying to tell all the tiny atomic magnets inside it to line up and point the same way. Magnetization just measures how well they listen. It's the strength of that internal alignment.
Next, we have magnetic intensity, or H. Now, if magnetization is the internal response, then H is the external effort. It's the pure, raw magnetic field that you're applying from the outside, from your coil of wire or whatever, completely separate from how the material itself decides to react to it.
So, how do we connect the external effort H to the internal response M? Well, we use something called magnetic susceptibility, or chi. It's just a number, but it's a super useful one. It basically tells you how suggestible a material is, how easily it can be magnetized. A big susceptibility means it lines up eagerly. A tiny one means it pretty much ignores the field.
And this is how it all hits together in one beautiful little equation. The total magnetic field you end up with inside a material, which we call B, is just a combination of the external field you're applying, H, plus the material's own internal magnetic response, M. It's the outside effort plus the inside reaction. Now, using that idea of susceptibility, how suggestible a material is, we can sort pretty much everything in the universe into three main groups, or as I like to call them, three magnetic personalities. Let's break this down. First, you have your diamagnetic materials, things like copper and water. Their susceptibility is actually small and negative. They're the contrarians. They get weakly repelled by magnetic fields and push the field lines away. Then you've got paramagnetic materials, like aluminum. They have a small, positive susceptibility. They're kind of easygoing. They get weakly attracted and pull the field lines in just a little bit. And then you have the superstars, ferromagnetic materials, like iron. Their susceptibility is huge and positive. They are strongly, powerfully attracted, and they suck in those magnetic field lines like a vacuum cleaner.
So what's the secret to ferromagnets being so, well, magnetic? It all comes down to something called domains. See, in a material like iron, the tiny atomic magnets don't just act on their own. They form little neighborhoods, or domains, where they all spontaneously agree to point in the same direction. Then, when you apply an external field, all these different neighborhoods snap into alignment together, creating one giant, super powerful magnet. It's all about teamwork.
And for a little mind-bending physics fact, check this out. Superconductors, those incredible materials with zero electrical resistance, are also perfect diamagnets. They don't just weakly repel magnetic fields, they kick them out completely. It's a phenomenon called the Meissner effect, and it's so strong it's what allows things like those magnetically levitating trains to float. How cool is that? So, after going through all of that, we land right back where we started, at the one core idea that separates the world of magnetism from the world of electricity. You can find a lonely positive charge, or a lonely negative charge, no problem. But magnetic poles, they're never single. They are always, always born in pairs. And that brings us to our final, lingering thought. A law like Gauss's law is amazing because it tells us that magnetic monopoles don't seem to exist. But it doesn't tell us why. Why does the universe work this way? The simple observation, something you can see just by breaking a toy magnet, points to one of the deepest, most profound unanswered questions in all of physics. Is there some even more fundamental law that forbids a lonely North Pole? And if we ever did find one, what would that tell us about the very fabric of reality?